so when we talked about steric interactions, okay, that is, if you have cases where you have you have particles, and on the surface of the particle you have some long chain molecules that are either covalently bonded to the surface, or they could be adsorbed onto the surface. Okay. So, if you have cases like that, then I had mentioned that there exists what is called as a steric repulsion. Okay. You can think about steric repulsion also as something called as osmotic repulsion. Okay. So, we will see what it actually means. Okay. So, when the polymer chains are in good solvent, okay, that means the polymer molecules are happy being in a solvent. Okay. Then you can say that when you say that the chains are swollen, okay, that means they are in a expanded configuration. Okay. And in a sense, that the reason that they are in an extended configuration, that means they do not like to be in contact with the polymer chains, they are happy being in contact with the solvent molecule. Okay. That means the chains essentially repel each other, right. So, now if you have a case where, so this is a case where the particles are sufficiently far apart. Now, this is a case where the particles have come sufficiently close to each other. Okay. Then what will happen is that as the two particles which are with these polymer chains which are attached covalently or adsorbed, when they approach each other, you can think about it as there is a local increase in the osmotic pressure force. Okay. What you can think about is, if I look at the region here, now there are many more polymer molecules in the volume, in the region between the two particles, than you have the polymer molecules elsewhere, right. It is exactly the reverse of depletion interaction, right. In depletion, we said that when they overlap, when you have polymers that are not adsorbed, okay, when you have a non-adsorbing polymer, I said that when the particles come sufficiently close, you get a region where the polymers are depleted, that means there are no polymers there, right. However, in the case of steric repulsion, what happens is something that is contrary, right. On an average, there is an increase in the concentration of polymers in the gap between the particles. Therefore, I can say that effective osmotic pressure force in the region between the particles, okay, that is inner, is going to be larger than the osmotic pressure force that is outside, in the region that is outside. Okay. So, because of which now there is going to be a force that is going to be in the opposite direction, okay, to what we saw for the depletion attraction case. That means the particles are going to be pushed away, right. Okay. So, therefore, okay, when they approach each other, the local osmotic pressure increases dramatically, okay, due to the fact that there is a competition between the polymer chains to occupy that volume, and this competition what leads to a repulsive interaction. Okay. And this is essentially a plot of the interaction energy as a function of separation distance. Okay. So, now there is a dotted line, that dotted line corresponds to the interaction where correspond to the case when you have absence of steric repulsion. Okay. There could be van der Waals or other kind of attractive forces in the system, that is this particular curve, there is a dotted dashed line, and however, this continuous line that you are seeing is where you have steric interaction present in the system, okay, and it essentially is going to, again depending upon the separation distance and depending upon the concentration of polymer molecules in the gap between the particles, is going to increase, right. So, that is a typical plot that you will see. Yeah.
Polymers
When I say polymer repel each other, you should think about it more like they are more happy being in contact with solvent molecules than with the polymer molecule. Okay, maybe you can think about along these lines. So that means I have a particle, okay, which is in a pool of solvent. Okay, it would rather prefer, because we are talking about a good solvent. Okay, the polymer would prefer to be in contact with solvent given a chance. Okay, if you talk about bad solvent, the polymer does not want to be in contact with the solvent. Therefore, the polymer interactions are preferred. So that's the analogy. Yeah. Yeah.
So this steric interaction, what is the origin of this steric interaction?
So the steric interaction, the only thing it does is, see, there are some, like say if you look at, okay, say that I have a system of particles, okay, and we know that we are always going to have this van der Waals attraction between the particles, right? Now, how do I get rid of such interactions? Okay, one of the ways we thought about is, if I take these particles, if I put them in a medium where the Hammaka constant of the medium and the particles are the same, then I can get rid of van der Waals interactions, right? Now, the other way of somehow negating the effect of van der Waals interaction is to look at a case where I somehow ensure that the particles would never approach the separation distance where the van der Waals forces become important. Okay. So, one of the ways of doing that would be by introducing some chains on the particle surface, okay, so that now the separation distance between the two particles is never going to be less than 10 nanometers, something like that, so that you do not have van der Waals attraction dominating in the system. Okay. One of the ways of thinking about the steric interactions could be in terms of osmotic repulsion. Okay, so that the fact that locally, so for example, so this phi star that is seen here is you can think about this as a grafting density, right? Phi star, it refers to the concentration of polymer molecules that is attached onto the surface. You can think about grafting density, right? Now, what will happen is, when they are sufficiently close, in the region between the polymers particles, the overall concentration is definitely going to be greater than phi star, right? Okay, so when that happens, there is the osmotic pressure imbalance again in this case. Only thing is, it is opposite to the direction that we saw for the depletion attraction case. Okay, that's the crux. Yeah.
Yes.
Now, it turns out that the steric repulsion depends again on the polymer configuration, right? Whether the polymer that is adsorbed or grafted onto the surface, is it does it take a shape like this, or does it take a shape like this? Okay, this is something called a brushed like configuration. Okay, this is something called a mushroom like configuration. Okay, these configurations are seen when the polymer chains or polymer molecules are covalently bond to the surface, and such configuration is when you have polymer molecules that are adsorbed onto the particle surface. Okay, so depending upon it will depend on the configuration of the polymer, it will depend on the grafting density itself, right? What is the number of chains per unit area that is attached to the surface. So it depends on a lot of factors. Calculating steric interactions is a little bit more complicated than the depletion because of all these effects, right? Because you would have to have an idea about the configuration of the polymer chains. You should have a definite understanding of or measurement of the grafting density, all of that. Okay, so I don't have any more stuff on steric repulsion. Again, the book that I mentioned does have sufficient bit of chapters on steric interactions. If you want to read more, you can go back and read up a little bit. So this is again a general like in any in any colloidal system, the total interaction potential will always be a summation of van der Waals plus W brush. In this case, W brush essentially corresponds to W steric, if you want to call it as. Okay. And the steric repulsion or W brush is going to be repulsive, right, that is this, and the van der Waals is going to be attractive. So, the whole idea of putting W brush is that, you know, or the steric repulsion is that, you know, the overall interaction would still be repulsive, right, that is your W total, okay, depending upon, you know, the configuration of the polymer molecules, depending upon the grafting density, everything. Okay. So, this curve could be shifted up or down depending upon what problem you are trying to look at. Okay. So, this is essentially to tell you that the total interaction in a case where you have steric repulsion is a summation of van der Waals interaction plus the interaction that comes because of the adsorbed polymers. Okay. Yeah.
W brushes between both the polymers.
No, this is actually so this W total is the particle interaction.
Yeah. So the brushes between polymer of one particle.
Correct. See, when we plotted this, right? Okay, let me do it this way. Okay, this plot. Okay, let's say that, you know, so we are worried about just two particles, right? And say that I want to calculate what is the van der Waals force of interaction between the two. Okay, so we know that, you know, it goes something like this, right? And if given that the particle size is r and the separation distance is d, we know that, you know, this basically goes as something like 8 times r divided by 6d, something like that, right? So, we know how to do that, right. Now what you have is, I have two particles, okay, on which I have these grafted chains, right. Now, I'm still talking about the particle interaction. Okay. Now, in this case, in the case of particle interaction with, you know, these grafted chains, okay, so it turns out that so if they are in a configuration like this, okay, of course, the interaction is going to be 0, right. I do not have any steric effects at all, right. Now, of course, that will happen for large separation distance, right. Now, when they start overlapping, so there is going to be again a lens that is formed, okay, and the moment that lens, you know, or the overlap occurs, then phi star is going to be larger. Okay. So, that is typically is happening here, right, that is where, you know, you actually start seeing some repulsion that happens here, and then of course, depending upon the overlap, you know, you are going to have an increase. In this case again, it is the interaction between the particles. Okay, it is the interaction between the particles with the grafted molecules on the surface. Okay. So, if you go back here, right, I mean, okay, similarly, right, if you look at expressions like this, this again is the particle interaction. It is nothing to do with, you know, the polymers on the, you know, in this case, of course, you have polymer molecules in the solution, okay, but these expressions are again the particle interactions is what we are talking about. Okay. Okay, I have a this is a recent paper, some nice work. So, you can what they have is this is a movie. It shows the formation of cubic crystals. Okay. And the way this is done is they have a dispersion of cube like particles, okay, and to that they add 0.8 grams per liter of PEO, polyethylene oxide, is a polymer, right, of so much molecular weight. Okay. That is the movie. So, what do you see, right? Definitely there were few individual particles to begin with. As time goes, you see that more and more the particles come, and this is a video microscopy image which tells you that there is a they talk about formation of a simple cubic crystal. Right? If you look at like it's a cubic crystal, right? It's a right. Okay, so that's movie 1, in which case a polymer has been added. Okay, everything is exactly same. Okay, all that is being done is I have a container with particles. Okay, and then to that you add a polymer, right? Particles. This is cubic particles, right? So again, an example where the depletion forces come into picture to form large crystals. This is another experiment where instead of I mentioned about I can induce depletion effects by adding a polymer, by adding a small particle, or by adding a micelle, right, solution. So this is an example where to a dispersion of cubes they have added a particle which is called a poly-NIPAM microgel. I had introduced this at some point when I talked about DLS measurements, dynamic light scattering measurements. I had mentioned that there are particles which can shrink or which can expand, depending upon temperature. So that's a microgel particles, and these particles at 40 degrees centigrade, p-NIPAM particles shrink, causing a reduction in the depletion interaction. So in this case, we know that the strength of depletion interaction depend on the size of the polymer molecules, right? Rg we've been talking about, right? So if I'm using p-NIPAM as a depletant, right? Or the p-NIPAM is something that is causing depletion interaction, depending upon the size of the p-NIPAM particle, I can tune the effective attraction between the particles, right? So and then what they do is they do an experiment where they heat the sample to they start with 20 degrees centigrade. So they start with 40, they cool it to 20, and again they heat it back to 45. Okay, this is a state where this is the crystals are already formed. Okay, I guess the temperature scale is not given, but you can imagine that they are heating up. Okay, so let's see what happens. So you should imagine that the crystals were already there. Now you can see that the crystals melt away. Okay, they all become individual particles. Okay, then you can recreate them. Let's come back here, somewhere here. So this is basically what is being done is I can work with a system of cube-like particles and this p-NIPAM, right? This p-NIPAM. So I can just subject that to heating and cooling cycles. I can tune the depletion interaction, right, depending upon their size. Okay, I am keeping the number of p-NIPAM particles same, because I'm not playing with that. I've kept this constant concentration of p-NIPAM particles, but just by making it either larger or smaller, I am able to control the strength of depletion interaction that leads to either the formation of a large aggregate or a crystal, or I can melt the crystal away just by tuning the dimensions. Okay, so I've just formulated a problem based on this. It's a tutorial problem. To an aqueous suspension consisting of, these are actually core shell cubic particles. So what they do is they form a particle which is made of hematite, okay, and then they coat it with a layer of silica, okay, and then if you put these particles in HCl solution, what will happen is you can remove the inner core, you get a core shell particle. Okay, this is hollow, that is silica. Okay, so it is a core shell cubic particle. The length of the cube is given, okay, and the shell thickness is also given, okay, and p-NIPAM microgyl particles of 65 nanometer are added to induce depletion attraction. They are given a schematic diagram. Okay. So, that is the cubic particle. You can think about a depletion layer. Okay. The size of this depletion layer is going to be Rg by 2. Okay. And this is when then when they are sufficiently close, there is going to be a depletion volume, right. Now, okay, so that is a schematic. Okay, the depletion volume is delta V. Now, the geometrical arguments can be used to show that the depletion volume delta V for the two cubes in contact can be given by this. Okay, can be given by this. Make some approximations and calculate the strength of depletion attraction as a function of separation distance in units of kBt. Okay. So, the following data has been given. The typical depleted number density is this, okay, that is 6.9 10 power 20 particles per meter cube, that is the, okay, and temperature of the suspension is also given to you. On that is, so you are supposed to calculate what is the strength of depletion attraction given these two conditions. The other question that has been that you can ask is, on increase of the water temperature to 40 degrees centigrade, the p-NIPAM microgyl particles shrink. Okay. So, then what will happen is your Rg is going to change, right. Then you are supposed to think about what would happen to the strength of depletion attraction. Okay. So, that is what has been asked to you. So, think of I will just post this problem, take a look at it, read up a little bit, we can discuss the solution in the next class, okay, which is essentially based on the work that is there in this paper. Okay. So, yeah, thanks.